Hello everyone, and welcome back to DevOps conference. And today we have Juraci, who is a contributor for OpenTelemetry project and maintainer of Jagger project. Hi Juraci, how are you doing?
Hi, very good. How about you?
I'm very good, thank you so much. It's really great to have you here. And
My pleasure.
it's really great. And to start with some small talk, can you tell us a bit how you get to OpenTelemetry, how you become maintainer of Jagger? I'm really curious about it.
Sure, yeah, absolutely. Yeah, so I started in this area a few years ago on a project that doesn't exist anymore called Hawkler. And we had a module within Hawkler called Hawkler APM, application performance management. And some years after that, when we were developing Hawkler APM or Hawkler, there was something called open tracing. So we started collaborating with open tracing, and eventually we realized that the modules weren't that perfectly a match. So we decided to do a rewrite, and at the same time, Uber had released their distributed tracing solution called Jaeger, and we decided to take a look and see if we could collaborate with them instead of just building something from scratch. And that's how we kind of got into this area of tracing, open tracing, and open tracing eventually became OpenTelemetry with the union of open census and open tracing. And for a couple of years now, I'm highly involved with OpenTelemetry Collector and OpenTelemetry in general. So I guess that's the short story of how I landed here.
That's really cool. And why it was important for you? Why tracing and telemetry was important for you?
Yeah, so I think first, distributed tracing is really cool. I think it is such a technology that that is so powerful, that allows you to understand so much about your software, not only about the operational aspects of it, like memory consumption and all the services involved in a trace and so on and so forth, but also the business side of it. Right. So if you look at the tracing data, you can infer so much knowledge about your business that I think there's a lot of potential. There's a lot of fun in there. So that's why I like distributed tracing, and I got into OpenTelemetry by means of distributed tracing. So OpenTelemetry right now is the de facto standard for distributed tracing, at least the tracing parts. And the collector is built in an architecture we're going to see later today. But it was built in such an architecture that it makes it very flexible, very versatile, right? So, and I think that power tied with with distributed tracing is really compelling. So I love working with the collector because of all the possibilities that it can give us.
Yeah, I see you're really excited. And we're talking today about diving deep into collectors, and I'm just cannot wait more to listen your talk. How about we'll get started?
Sure, absolutely. So I can get started. Welcome again to OpenTelemetry Collector Deep Dive. My name is Juraci Paixão Kröhling. I'm a software engineer at Grafana, and I work on the OpenTelemetry project. Right. So, and today we're going to talk all about OpenTelemetry Collector. But before talking about the collector, I'd like to give a few words about OpenTelemetry itself. And after that very fast introduction to OpenTelemetry, we'll see how the collector works and what it is, where we can use it, and how it is architected. Then we see a couple of projects that are around the collector or the same ecosystem, the same space as the collector. And we then go deep dive into deployment patterns. So how can we use the collector in production for building a pipeline, a telemetry pipeline? So we have a general purpose patterns like the basic pattern, normalizer per signal. We have patterns to use with Kubernetes, like when to use sidecars, when to use demo sets. And we have some enterprise patterns as well, like multi-cluster, multi-tenancy, and load balancing. We finished the session here today with some advanced topics. So we have about 15 to 20 minutes where we are going to assemble our own OpenTelemetry collector distribution. So we're going to build one collector for us. And we are going to then extend our distribution, or we're going to extend OpenTelemetry Collector with one component of our own. So we're going to build a processor that adds a specific tag to all the spans that are processed in the pipeline. Now, we should be having a couple of minutes for a Q&A during the session, but if not, I'm more than happy to take questions in the room after the session here. All right, so that's it. Let's get started, and let's get started with what is OpenTelemetry. Right, so OpenTelemetry is a collection of tools, APIs, and SDKs. If you open the OpenTelemetry.io, you're going to see this definition here. And use OpenTelemetry to instrument, generate, collect, and export telemetry data such as metrics, logs, and traces to help you analyze your software's performance and behavior. Now, if we parse this statement here, and if we try to understand it, it then becomes clear that OpenTelemetry isn't one thing, isn't one project. It is actually a set of projects. And I like to categorize them in three different areas. So the first one is standards, specifications, and conventions. And then we have in the middle the client instrumentation APIs and SDKs, and then we have the middleware. Now, on the first box, so on standard specifications and conventions, we have again three main types of projects within that box, and I guess the biggest one, the one that is more visible, is OpenTelemetry API and SDK. Right, at least more visible to users, to project and business developers. And those APIs and SDKs, they are defined, they have a specification, and so that people who are developing an API and SDK can use that specification to know what to implement. So for instance, perhaps I'm a fan of a specific programming language that doesn't have an API yet, that doesn't have an SDK. So I can use the API and SDK specifications to implement an API and SDK for that specific language. Now, another type of document that we have are the semantic conventions. Now, the semantic conventions, they are a document telling us what should be part of the telemetry data that we generate. Now, imagine that you have a Go and a Java microservices. It would be a shame for for us to get into our telemetry system, our dashboards, and have to think about what is the language that each one of our services are written in, so that we can query the telemetry data from them. Right, so the semantic conventions are there to say, no matter the language that you're coding your application into or in, you should be, if it is an HTTP REST service, for instance, then you have to provide what is a HTTP URL under this telemetry metadata here. Or you have to provide the HTTP status code under this key, and so on and so forth. Right? And the same exists for database operations, for message queues, and so on and so forth. Again, the idea is I should be able to query my telemetry data, no matter the language it was written in. It doesn't matter which frameworks were used. That data should be consistent. And that's what the semantic conventions are dictating here. And finally, we have another specification called the OTLP, which is the OpenTelemetry Line Protocol, right? Or just simply OpenTelemetry Protocol. And that is an interface description language, an IDL, specifying how data should look like and what endpoints should implement. So on technical terms, what it means is OTLP is just a set of proto files located in a specific repository that you can look at and implement. Right? So it defines both the message, like the payload, and the envelope or the service. Right? So you can implement it both as a client or as a server. So as a client, perhaps you have a specific use case that you don't want to use API and SDK to generate your data, your telemetry data. Perhaps you are doing on a very limited scenario, on a very limited device, so you want to generate the OTLP data on your own. So you can just generate that. You generate the client interfaces as well, the client for OTLP, and you send this data to an OTLP compatible endpoint somewhere. Right, so you don't actually have to use API and SDK to generate OTLP, and you don't need them to send this data out to an OTLP compatible backend. Now, on the other side of the equation, we have the server, OTLP for the server side, And what it means is I can implement an OTLP endpoint without actually having to care about anything else, right? So I can just implement the endpoint, and I'm ingesting OTLP into my backend. Now, this is typically relevant for observability providers or monitoring vendors out there, right? So it's not something that we would implement ourselves. It's important to know that it exists, and it's important to know that it is one standard that we can use for interchange of data. All right, the second type of projects that we have, or the second bucket, is client instrumentation APIs and SDKs. And those are the things that we use on our daily basis, right? So as a business developer, as a product developer, I would look into OpenTelemetry API to instrument my services. So I can use the API to tell, this is where a span starts, this is where a span ends, or this is what I want to record as a gauge, this is a latency that I want to record for this operation, and so on and so forth. Now, the OpenTelemetry SDK, it is it's like the batteries behind the API, right? It is implementation. It is the part or the component that knows how to actually collect the data, how to store it in memory for some time, perhaps buffering it, and how to send this data out of the process. So this is the role of this SDK itself. In general, most of your application would be in touch with the API, and just an initialization code from your application would be dealing with the SDK. Now, then we have the instrumentation libraries. And instrumentation libraries, there are libraries that we can use, that we can add to our application, and they are going to hook into parts of our stack. Right, so imagine that you are a Java developer, you are building an application based on, Spring Boot, and you don't actually want to start instrumenting your application exhaustively, right? So you can use the instrumentation library for Spring Boot, and it will then inject the right instrumentation parts into your stack. Meaning, on the server side, it's going to inject a span starter, which is then going to close the span whenever you write the response to the client. And it is also going to inject an interceptor to your HTTP clients, so that whenever you call an external service, the context is automatically propagated. So you don't have to care about all those parts on your own. Now, a second type of instrumentation libraries, or in specialization of that, are the auto-instrumentation libraries. Right, so some languages like Java or Node.js, they provide an auto-instrumentation possibility, meaning I don't actually have to instrument my API at development time with the OpenTelemetry API. I don't have to instrument my application using instrumentation libraries during build or packaging time. I can use the auto-instrumentation to instrument my application at runtime by doing, in case of Java, by doing bytecode manipulation at runtime. Right? They might use the instrumentation libraries behind the scenes, but they don't actually have to. So the idea is, if I have an application that is legacy application that I don't have the sources anymore, or if an application that is running for quite some time, and I don't want to touch it that much, I can just add a Java agent or an auto-instrumentation library that would then extract telemetry data out of that application for me. All right, but we're really interested about the collector, and we've talked too much about the OpenTelemetry side of things, and we want to focus here on the middleware side of the project. And within the middleware, we have the OpenTelemetry Collector. And I realize that I've mentioned OpenTelemetry Collector a few times already, but I haven't given you a formal introduction yet. So here it is. So if you go to the same website that we've seen before, OpenTelemetry.io, and you go to the documentation collector, you're going to see this statement here. Right? So the collector is a vendor-agnostic way to receive, process, and export telemetry data. Now, this statement here, it already gives us a hint on how the collector is architected. Right? So we have receivers, processors, and exporters. That's the main architecture. That's what you have to understand about the collector. And if you figure that, or if you picture that, you understand 90% of the collector already. Now, on the same web page, on the same page of in the same documentation page, you'll find this image here. Now, this image here might be a little bit overwhelming at first, so let's break it down. So on the left-hand side, we have three boxes. So we have receivers. We have a box with OTLP, we have a box with Jaeger, and we have a box with Prometheus. Those are all receivers. Those are all components that are responsible for getting data into the collector process. Now, they might be active or passive. So Prometheus might be doing some scraping, so it might be going out some processes, whereas the others might be passive. So they are receiving data from clients, right? Which is the case for Jaeger and OTLP. Now, receivers might also be single signal, meaning they only care about traces or they only care about metrics, but they also might be multi-signal, right? OTLP, for instance, is able to ingest traces, logs, and metrics. Now, on the middle here, we have two pipelines. We have two sets of processors. One with the yellow line is a traces pipeline, and the one with a green line is a metrics pipeline. Now, the first one, we have a set of processors starting with a batch, and then we have some other processors, and then we have attributes being the last one in this pipeline here in this queue. And then data goes to the exporters. Now, for the second pipeline, we have batch also for the first processor. Then we have a lot of other processors, and finishing with a filter processor. Now, the filter and attributes, and the name of the processors, those are just examples. Now, once data gets from the last processor, they reach the exporters. And again, we have exporters that might be multi-signal or working for a single signal as well. For instance, OTLP works for all the three signals, so logs, metrics, and traces. Jaeger is only for traces, and Prometheus is only for metrics. And again, they might be passive or active, so Jaeger is actively sending data out to a Jaeger collector somewhere. OTLP is actively sending data to an OTLP-compatible service out there, and Prometheus might either be doing remote writes, or it might be just exposing an open metrics endpoint for an external Prometheus-compatible processor to scrape data out of that. Now, if you're paying attention to this graph here, you might have noticed one thing that we haven't talked about, and it is at the middle of the picture, top, we have extensions. Right? And extensions, they are not tied to pipelines. They are things that extend the collector in ways that are not really part of pipeline. So they might be debugging interfaces like pprof and zpages, or they might be providing health check endpoints for load balancers and Kubernetes, for instance, or they might be extending the collector in some way, for instance, by implementing a different authenticator interface. Right? So perhaps we have our own authentication requirements, and we implement our own authenticator, and we register that as an extension. All right, so that's it. That's the collector. So we are seeing here a picture of one single process with two pipelines, 3 receivers, 3 exporters, and a few processors. All right, now besides the collector, we have a couple of other projects within the realm of middleware. And the first one is, the OpenTelemetry Collector contrib repository. And the contrib is perhaps the biggest repository of them all. And it is where non-core components reside, such as the routing processor or the load balancing exporter or vendor-specific components. Now, a second a project or a second component that we have is the OpenTelemetry Collector Builder. Now, the Builder is a tool, and we're going to use it later, that allows us to build OpenTelemetry Collector distributions. So we can specify in a manifest, we can specify which components we want to be part of our OpenTelemetry Collector distribution. And then we have the operator, which is used in Kubernetes. So it is a Kubernetes operator managing OpenTelemetry Collector instances. Now, if you're deploying your application on Kubernetes, and I bet that most of you are, you can use the operator to not only manage the collector instances, but also to do auto-instrumentation of your workloads. Right? So just recently, on the latest version just released a few days ago, we have the ability to auto-instrument Java workloads. So you annotate your workloads, your deployments, or the stateful sets, and so on and so forth, by saying, I want auto-instrumentation to exist for this workload here. And then the OpenTelemetry operator is going to then inject or change your deployment at runtime, your pod spec at deployment time, to add the auto instrumentation libraries to your Java application. It's really cool. You should try it out and send us feedback if you do. Now, that's my introduction to the collector. I think we should now talk about patterns. So how to use OpenTelemetry Collector in the real world for your telemetry pipelines. Now, the first pattern, just to get us warmed up, is the basic pattern. And on the left-hand side here, we have our application, our workload, and our application is instrumented with OpenTelemetry SDK, or it might be instrumented with some instrumentation library. OpenTelemetry SDK is one of them, but perhaps it is OpenTracing plus Jaeger client, or perhaps it is Zipkin, or whatever your application has instrumented. Now, the important part is they talk the same language. The collector and the instrumentation library, they talk the same language. Data goes from your application, from your workload, to the OpenTelemetry collector, which then has the possibility or the ability to do some processing on your data and send this data out to an external system like Jaeger. Now, Jaeger here is just an example. It could have been a matrix instrumentation sending data to a matrix backend, but the basic idea is this one here. So we have the collector as a proxy, as someone in between your workload and your actual backend. Now, it is good for abstracting where to actually send your telemetry data. And it is very good for doing extra processing between the workload and telemetry backend. Right, so perhaps you need a specific feature that is not supported by your backend. So you do this extra hop here to do that processing before sending data out. And it is quite useful when you are when your workload is already instrumented with some library that you don't want to change right now. So you don't want to change that application, so you just do some processing in the middle and send data to the final backend. Now, you should not use this pattern, or you should not use a collector at all if you don't actually have to, right? I mean, that goes without saying, but just because it is a shiny new tool is not reason good enough for you to use. Let's remember that every extra hop is a chance for things to go wrong. That's the first rule of distributed systems, right? So, you know the rules of distributed systems, but if there's one thing that we know about distributed systems is that they fail, and they fail all the time. So adding an extra hop is increasing the chances of things going wrong. All right, so the pattern is still number one, but it's a variant of the first case, and I call this one here the fan-out, is where we have a workload, and again, it is instrumented with some instrumentation library, sends data using some protocol to the collector. And the case now here is the collector not only sends data to one backend, like Jaeger, but it also sends data to a second backend. And that might be a vendor, it might be a different open source system, or it might be, your homemade solution for traces. Now, I think you can see the potential here, but you should use this pattern here when trying out different open source solutions and or vendors. But more importantly, at least to me, is that you can use this pattern to retain data ownership, even when your main observability tool is a SaaS. Right? So sending your data to a system that is internal to you is very important for you to still own your data. If you just send your data to a SaaS provider, you don't own your data anymore, most of the time, right? Now, you should avoid this pattern when you are not trying out different things, or when you don't have a need for sending data to two different places, because I think it is obvious, but the double the data that is sent out, the double it costs in terms of networking and perhaps even in terms of storage. All right, so use this tool, or use this pattern to try it out and settle on a specific set of solutions, and then dial down, right? So I guess that's the main idea here. All right, so pattern number two is a normalizer pattern. And on the left-hand side, we have our workload. It is instrumented with two different instrumentation libraries. So one for metrics, one for traces. Perhaps they were done at different times. Perhaps they were done even by different people. So perhaps we started with a metrics instrumentation like the Prometheus client, and then some other developer a couple of years later decided to try distributed tracing out and added distributed tracing instrumentation using OpenTracing plus Jaeger client. Now, the problem with that might be that the metadata from your metrics are not similar to the metadata from your traces. So you might not have data that can be correlated or that cannot be easily correlated. So in that case, instead of changing your application, you can use the OpenTelemetry Collector with a couple of processors like the attributes processor and the metrics transform processor to normalize the metadata from the data points. Right. So, for instance, your metrics data points, so your time series, they might contain a label like the DC for the data center and a specific value, whereas your spans might contain a data center instead of DC within the spans, right, as tags on the spans. So you might want to use the OpenTelemetry Collector here in the middle to normalize that by using, I don't know, DC for everything or data center for all of them. So that when data goes to the final backend, we can then query for the same types of attributes on both backends, on Jaeger and Prometheus in this example here. Now, this pattern here is good for ensuring that different data points have the same semantics for the same things. And it is good for a situation where it's hard or undesirable to fix the problem at the source. Now, it goes without saying that if you're placing the collector in there to fix metadata, it is doing processing that it potentially doesn't have to. Right, so avoid this pattern when you have too many things to normalize. That's typically a sign that you have to go back to your application and fix a few things there. So it might be better, in terms of cost, CPU, and memory consumption to fix things at the source, so to generate the right data in the first place. All right, so we are now at the pattern number 3, and we are talking about now Kubernetes. We have 2 patterns for that, and the first one is sidecars. I trust that you know what sidecars are, but just to recap, a sidecar is a second container in a pod. Right, so our pods or Kubernetes pods, they typically have one container, and a sidecar is a second container or an extra container to your pod, typically taking care of a cross-cutting concern, like monitoring agents such as our case here, or security sidecars and things like that. Now, in our case here, we're using sidecars so that we offload data as fast as possible from our workload out of that process, so into our collector. Now, the point here is that the collector is specialized in storing this data in memory for some time and resiliently sending this data out to over the network. Now, a key thing to remember here is that everything that is inside a pod, so if you have like 10 containers or 2 containers, they're all part of the same local network. So everything that we have here between the application and the first layer of collectors, like the sidecar collector, is local network. So the chances of the network failing there is really low. And because it is local network, again, it is very fast. So we get data out of that process, almost instantly. And from the collector, we can then take care of doing retries and backups and, batching data and doing sending data out in a more organized fashion. Now, each sidecar may potentially have its own configuration. So if an application in my specific namespace, it is more important, then I can have a special configuration for that application. But typically, we would have one configuration per namespace, right? So all the workloads, all the applications on that specific namespace, they would share the same configuration. Now, perhaps we have a tenant per namespace kind of scenario. So we can then potentially have one OpenTelemetry Collector configuration per tenant, and then multiple instances of the collector, one per pod. Now, we may also have like one configuration for the whole cluster if you want. And the advantage of having and that is, if it fails only for that specific application, right? So to have the collector as part of the pod. Now, those sidecars, they all send data to a central OpenTelemetry collector in the cluster. So perhaps we have a namespace named observability, and we have a collector in there, and a tracing backend like Jaeger deployed on the same namespace. So the connection between the sidecars and the central collector is potentially remote. And that remote collector then decides where to send data to. Now, this pattern here is good for quickly offloading telemetry data from your application to a local process, which is a sidecar. It's good for a fine-grained control over the configuration for each pod spec or namespace. And client-side load balancing is better when there are multiple clients, of course, especially for long-lived connections. So this is a tricky one. Things that we sometimes forget is that if we have like only 2 sidecars or only 2 instances of the collector very close to our applications, and those 2 instances are connecting to a cluster of OpenTelemetry collectors, like a centralized, containing like 10 replicas, then 8 of those replicas are going to stay idle, right? Because we only have 2 long-lived connections in there. And only when that connection fails, a client will go to another collector. But at any given time, we have only, at most, the same number of connections as we have on the clients. So the more clients, the more connections, the better load balancing we have from the client side of things. Now, avoid this pattern where the overhead is not acceptable. Now, each sidecar may need at least 20 megabytes of RAM. Now, I've seen sidecars with 5 megabytes, so take between 5 and 20 megabytes as the size of the sidecar. And if that's not acceptable to you, then you should consider the alternative that we're going to talk about in a couple of seconds. Now, you should avoid sidecars as well when you cannot manage the sidecar configuration with something like an operator, right? I mean, if you have to manage the configuration of or if you have to manage the sidecars on a per application basis, that's just too much of a management overhead. All right, so whenever you change a configuration, you have to remember which sidecars you have to restart or which pods you have to restart. All right, so the second Kubernetes pattern that we have is using daemon sets instead of sidecars. And in the example here, we have 4 pods. And in the previous example, we would that would mean that we have 4 sidecars. And in the example here, we have only 2 sidecars, or only 2 OpenTelemetry collectors acting as an agent here. And it happens like that because, in Kubernetes, a daemon set is, we specify a daemon set, and then we get 1 pod per node in our cluster. And it still has the same advantages of the collector, of the sidecar approach in some aspects, like it is still local connection. So the connection between the local pods and the local collector has a very high chance of succeeding. Right? It is very fast. It's only a software-defined network here that is taking care of the communication. So it is quite reliable. Now, the downside is, depending on the protocols that you use, it might not be that straightforward to determine from which namespace and from which workload data has been coming from. Right, so from the collector side, if you're using OTLP or Jaeger, for instance, then we have a client making a connection to the server, and if the client is not authenticating with the server, and if the client is not adding the client metadata to the communication in any other way, then it's very hard for the collector, local collector here, to determine who the client is. Right, so doing multi-tenancy, for instance, is harder, not impossible, but harder in this kind of case. Now, the common thing between daemon sets and sidecars is that we send data from the local collectors to a centralized OpenTelemetry collector, perhaps in a cluster, perhaps external to the cluster, that will then take care of sending data to the final destination. Now, we have the second layer of collectors here, taking care of sending data to the final destination, because if we change our pipeline in some way, if we change vendors, if we change the open source solution that we want to use, we only change one layer of collectors. We don't have to change all of the sidecars or all of the daemon sets. We don't have to do a new rollout of them just to change our pipeline. So that's the main reason for the second layer of collectors here. Now, this pattern is very good for quickly offloading data, just like the sidecar. But less collector instances mean also less maintenance and runtime overhead. Right? So if you are worried about the memory and or runtime and maintenance overhead of sidecars, you should really take a look at daemon sets. You should avoid daemon sets if you need features like multi-tenancy. Right? So if you do need multi-tenancy, you have to think twice about how to achieve that in a way that is secure and in a way that you don't require the client to tell us who they are, and just trusting that. So you have to verify that. And it is also you should also think twice before using daemon sets if it is not acceptable to lose your telemetry data in case a daemon set pod, or in case of a pod, fails or crashes. All right, so if a local pod to a node fails, it means that potentially all of the telemetry data for that specific node is going to be lost for some time. All right, so pattern number 4, we have a load balancing pattern. And in this case here, we have two layers of collectors. So one is the ones receiving the data right before the backends. So we have the blue and the green collectors here. And we have our workloads on the other hand, and in the middle of them, we have a load balancer. So the load balancer is also an OpenTelemetry Collector instance, just configured a little bit differently. Now, perhaps we should talk a little bit about load balancing in general when it comes to telemetry data, because it is not that simple, it's not that straightforward. Now, it might be simple for logs. So logs are individual events that we receive from our applications. So if we receive different log entries from the same application or from different applications, it is typically okay to just round robin them, right? So send a 50% to the first collector and 50% to the other collector, and that's fine. Now, for metrics, things get a little bit complicated, because if we are doing aggregations at some levels, we have to consider them when doing the load balancing. At the same time, if we are, we cannot just do load balancing of metrics based on our origin of the metrics. So we may, what I want to say is we might have a source of data that has like 10 time series, and another workload, another source of data has, I don't know, hundreds or perhaps even thousands of time series. So just balancing based on the source of data, or the client in this case, is wrong, right? So what we want to do is, probably we want you to send 50% of the time series to the first collector and 50% of the time series to another collector. Now, when we are talking about tracing, we have another scenario, a third scenario, and that is, we might need to have a complete view of the trace at the collector, at the blue and green layer here, right? So perhaps we are doing tail-based sampling. Perhaps we are doing some extra, like using a span matrix processor that requires a view of the whole trace. So we cannot send parts of the span or parts of the trace to one collector and parts of the same trace to another collector. We have to ensure that all of the traces for the same trace are going to the same collectors. And to achieve that, we can use a load balancing exporter that looks into the spans, looks at the trace ID within the spans, hashes it, and determines to which backend I should send this data to. So we have a consistent hashing for the trace ID, having consistent outputs of the destination. So use this scenario here when you need to load balance whole traces to collectors that need a complete view of the trace. Right? So you have to know which processors and exporters or which components you have at your backend to determine whether you need the load balancing. Avoid this case when you just need a simple load balancing. Right? So if you're doing if you're not doing any of the processors or components that require a complete view of the trace, then you're better off with a off-the-shelf router, or a load balancer, right? So perhaps a gRPC or perhaps a plain HTTP load balancer would do. All right, so pattern number 5 is a multi-cluster. It is very similar to the ones from Kubernetes that we've seen, but they are more generic, so they're not tied to Kubernetes. They're just similar in the way that we have the first layer of collectors as agents, the second layer of collectors as local to the cluster. But now we have a third layer of collectors on a control plane cluster. Right? So that control plane cluster would receive data from all of the clusters. Now, the important thing to note here is we are doing communication over the public internet, potentially. So we need to ensure that data is secure. So it is both encrypted in the pipe, and authentication is happening either via mutual TLS or by authentication mechanisms. Now, this pattern is good for centralizing your telemetry data collection across different clusters. And for running things like business analytics on all of your telemetry data. So it kind of implies that you send either all of your telemetry data there because you need all of the data, or you are doing a sampling of your data, you are doing aggregations at the individual clusters, and then sending only the results of those aggregations or sending only interesting traces out to the control plane cluster. Now, avoid this scenario when you can have your control plane to query data directly on individual clusters. So imagine that on your control plane cluster, you have your dashboard set up, your dashboard instance in there, and you can configure your dashboard to query data from the individual clusters instead of waiting for data to get into this specific cluster. Now, the reason is we typically query way less than we consume. Right, so we generate a lot of data, but we read just a bunch of data points. So it's probably cheaper to go to those individual clusters looking for data than having data sent to the central collector. Now, avoid this case here when networking costs are concerned. Right? So by default, you should not be doing multi-cluster unless you actually need it. And pattern number 6 is a multi-tenant pattern, and I kind of did a small joke here with OpenTelemetry Collector as a service, and two sites here, so acme.com and ecorp.com. In the real world, those would be more likely to be a IT department or an observability team within a company that handles or that manages a set of observability backends, like a tracing backend and a metrics backend. And the companies here, like acme.com or ecorp.com, would be internal departments. Now, they're still generating data, they're sending data to the central location, and they need to be charged back based on the resources they consume. Right? So we still want all of the data getting to a central collector within our realm, within the the observability team's realm, and based on the metadata from the requests, we're gonna route data to different exporters. So perhaps data from Acme is going to land at a Jaeger instance for Acme. Perhaps eCorp has a Zipkin instance. Perhaps another department is using a specific vendor. And perhaps for other services, they might not care about tracing data at all, just metrics, for instance. Right, so you can use this pattern here to route data based on tenancy or tenant requirements. Now, use this one here for small deployments where a central collector processes all of the telemetry data for all of the tenants. Now, central tenants, this is good for central teams to handle telemetry data from multiple departments, perhaps multiple clients as well, but I see this one here mostly as within a specific company. Now, avoid when you are able to afford one entry point per tenant, because it's easy to manage, right? So you avoid a single point of failure. Now, the last pattern that I have is a per signal pattern. And in this case here, and I think it is not so much of a pattern. I think it is really an advice for you. And the advice is don't use, at least not now, and perhaps not in the future, don't use the same telemetry pipeline as a whole for all of the signals at the same time. right? So apply the other patterns, so process data as you wish for, for normalizing data and so on and so forth. But keep in mind that the different signals, they have different requirements, and one can have influence on the other. 2 examples. First one is metrics. Traces are very stable for the collector and for OpenTelemetry in general, but metrics are not that stable yet. Right, so a problem in the metrics pipeline for the collector can bring your distributed tracing pipeline down. Now, the other example is, whereas metrics are aggregated, data can be reduced to a very minimal, and the memory consumption of a lot. You can process a lot of metrics with minimal memory footprint. It's not the same for traces. For traces, you need every single data point is individual. You have to look at, or you have to at least see all of them and potentially export all of them. So you cannot aggregate them. You cannot group them in any meaningful way as to reduce the memory size of it, or the byte size of your workload. So what it means is you end up with a high memory consumption that may affect your metrics pipeline. Right, so at some point in your pipeline, do branch out, do go, these metrics go here and traces go here. And so this is very good for isolating failures on production environments. Of course, it is overhead when you are doing, for development or staging environments. So don't do that for those cases. It is really useful for production. All right, so that's the end of the second part, and let's get started with customizing your OpenTelemetry Collector experience. And we'll start by building our own distribution. Now, to do that, we need a couple of things. So we need a manifest.yaml file that defines how our distribution looks like. And then we need the OpenTelemetry Collector Builder tool, or OCB as it's aliased in the example here. But why would we want to do that? I guess the reason is we have only 2 distributions right now. We have the core distribution with only a few components like the OTLP exporter and receiver, Jaeger exporter and receiver, Prometheus exporter and receiver, and a few processors. We don't have many more than that. Right? Now, if you need something else that is available in the contrib repository, then you have to use the contrib distribution. And the contrib distribution is everything under the sun. So it's a 100 plus megabytes distribution, which is not very suitable for sidecars, for instance. So in that case, you might want to build your own distribution to create a slimmed down version of contrib, or perhaps even using a component that you build on your own and is available on your internal repository. So those are reasons to build your own distribution. So let's do that. So let's build one of those distributions. We have here an example of a manifest, and a manifest has 2 main parts. So the first one is a metadata for the distribution itself, and the second part are a list of components that we want as part of our distribution. Right. So let me. The name of our distribution is going to be oops, and we're going to generate the sources under the / build. We're going to base our distribution on the 0370 of the collector, and our distribution itself is going to be on version 100, which is a bad idea to have 100 based on a non-stable version or a non-1.0 version, but that's okay. And we have only one extra exporter, and that's the Jaeger exporter on version 0370. So that's it. Let me open the terminal here within my code editor. So I am within the DevOps directory, and in here I do have my manifest.yaml file. So let me build it. So OpenTelemetry Collector Builder and config manifest. All right, and it's compiling, and it has compiled already, and we have now this binary file. Now we can run it, and we have, oops. I don't know what's going on, but it should work. And then I pass the config file that I want to run with my distribution. And the config file is a regular OpenTelemetry config file. Let me close this one here. If you've played with OpenTelemetry Collector before, you know this file here already. It is, we have a list of extensions, which is empty in our case. We have a list of receivers. We only have OTLP. We have a list of processors, empty. And we have a list of exporters. In our case, we only have Jaeger on the gRPC port for the collector. And then we define the service or the process of the collector. We define which extensions we want to use, and we don't have any extensions here. And we define the pipelines. We have only one pipeline, that's the traces pipeline. And for this pipeline, we tie the OTLP receiver with the Jaeger exporter. All right, so that's it. Let's open the terminal again. Let me maximize it. Let me clear my screen. Okay. So that's it, config, hotel, and it's ready. So it's connected. It says that it's connected to Jaeger, so everything's running. So I do have Jaeger running here in the background that I started before this presentation. And I have here a tool called a TraceGen that is part of the OpenTelemetry Collector contrib. So I just go to the TraceGen and let's generate some data. So go run OTLP insecure, because we don't have TLS enabled. And that's it. So it generated one trace, right? So one trace. So if we open our Jaeger UI in here, and if I load again, I see a TraceGen service. And if I find traces, I have one from a few seconds ago that has this. Right. So that's it. So we generated our own distribution, and it works. Right. So that's good. So again, it's very simple to do that. You just need a manifest file specifying how your distribution should look like. All right, so now we should proceed now with building our own component. And a component has three main things. So the first one is a config, which is our interface with our users. So the users would define the config for our component. And we have the component code itself, and we have a factory that ties the component with the collector. Now, for our demo here, we're following those steps. And I have those same steps here in the code editor, so I'm not going to read them out. But it's important to mention that I'm skipping the last one here. So the last one is a bonus point, so metrics. It's where you create metrics related to your component. Right? So make sure that you add enough telemetry to your processor or to your component to understand what it's doing in production. All right, so let me go back to the demo terminal. Let me stop the collector from there. And what we're going to do now, let me open the README. So those are the steps that I had on that slide. Right, so we have a create a Go module. We have create a config, create a processor, add the logic, and create a factory. So that's what we're going to do. I have all of those steps as branches here locally. So I'm just going to do, so where I am, let me open the DevOps processor. And let me check out, so this is my directory. So I only have a README file at this point here, right? And if I check out the step number 1, I get a Go file. And for Go developers, it's as basic as you can get, just specifying the Go version and the module. All right. Our step 2 is to create the config.go file. And the config has this one here, right? So it's just a boilerplate. We just specify config struct that embeds some specific construct. We don't have to understand this one here that much. We just have to understand that we have a processor settings, and we have for processors, and we have other settings for other types of components. Now, if we were to add specific config entries for our processor or for our component, we just add here like a string, name, and map structure, and so on and so forth. But that's not the case. Right? So we don't need any extra configuration for our component. Now, our third step is to create a processor.go file. Now, that one has two interesting parts. One of them is the capability. So what can our processor do? And our processor is going to change data. So we signal the collector that we mutate data. And this is where our processor code or our logic will reside. And we just have to specify function with the specific signature for now. So the name doesn't matter that much. We have just to have this signature. For this initial implementation, we are just returning the same pipeline data that we received and no errors, right? So nil errors. Now, when we implement the code, this is how it looks like. We're just iterating over all of the pipeline data for the traces. We're getting all of these spans, and for each span, we are inserting a new attribute called a scene add with the value dev-oops. All right, so basically, every single span flowing through our collector is going to be enhanced with this attribute. And that's it. So that's what our processor is doing. So this is our business logic. Finally, we tie them all together with a factory. And the factory here, step number 5, we just have to specify first what is the name of our processor when it comes to the configuration. So this is the name that users are going to make use of when configuring on the hotelcall.yaml file in our case. Now we have to have a function named a new factory that returns a processor factory. And in our case, we're going to use a helper for the factory that creates a proc type, create a default config, which is just boilerplate in our case, and specifies what is a tracer factory. And we implement this function. The name, again, doesn't matter that much as long as we pass it here. What matters is a signature. And this function will receive the configuration for our component. So everything that we define within DevOps node is going to end up here. In our case, we don't care that much because we are not going to use this configuration. We receive the next consumer, so who should be called next in the pipeline. And we have to specify what our function that does the processing of the traces. So this is our business logic, and we specify the processor capabilities. This is the one that we say that mutates data is true, and that's it. That's pretty much it. Our component is ready. It builds. Ideally, we would have metrics for that, but now we are ready to reference that in our manifest file. Right, so we can do like processors here and go mod, and we copy the module here. And we paste it here. This is Go module, so we have to specify version, which doesn't matter that much because its code is not published anywhere. And we specify replaces directive here, saying that for this module, we want to replace it with a local directory like this one here. Right, that's it. So again, for Go developers, this is familiar. So this is a Go mod entry, and this is a Go mod replaces entry. So this is should be familiar to you. And with that manifest up to date, let me maximize here. Let me clean my screen, and let's build another collector distribution. Perhaps I should go to one step back, one directory back, and OCB. So let me call OCB. That's it, the manifest. Now we have a new binary there, and we can now go to our OpenTelemetry Collector and specify our processor. So oops, that's all we need in here. And then we tie here as well. So oops. All right. That's it. Let's maximize the screen again, and let's start the collector with our configuration with the DevOps step. This one here, we have everything ready, and let's now generate a new trace. Right, so we generated a new trace. Let's go back to Jaeger, and we have a new trace here created a few seconds ago. And if we span them all, we see that we do have an attribute scene add DevOps. All right, so that's pretty much what I had for you today. I hope you enjoyed. And those are the key takeaways from this presentation. Right, so first, OpenTelemetry has different sub-projects in different areas. The collector works as a middleware, abstracting the telemetry backends from your workloads. Now, the OpenTelemetry Collector has a lot of components for you to experiment with. Now, mix and match collector instances with potentially different configurations. That's all the patterns are. So the patterns is just about mixing collector instances with different configurations. Now, use the patterns from this presentation to derive your own patterns. You've seen that extending the collector isn't that hard, and that building your own distribution might be a good idea depending on your use case. Thank you very much, and I'm ready to take your questions on the separate channel. Thank you very much.
Thank you. Thank you so much for presentation. It was amazing. A lot of very good information. Thank you so much, Jesse. And I think we'll take major questions in discussion. And I have probably one of my questions for you here. If you we will pick one of the patterns which you presented today, which one of your favorite here? Which one you will say, okay, here's my go-to strategy which I start from, and then
I think
pick another one.
The second one, so the fan out, is the one that I end up using most of the time. Right, so sending data both to the logging exporter, for instance, at least when developing, sending data to both the logging exporter and to Jaeger. So if anything is not working, then I know that the problem might be in this pipeline here, or the problem might be on that exporter there. So I think it is the one that I use the most on a daily basis as a developer. Now, when deploying things, I really like the sidecar pattern. I mean, the sidecar pattern is such powerful, and it works just seamlessly with the operator. So the operator can apply the pattern for you automatically. So that's really cool.
Okay, cool. Thank you so much. And I would propose us to move to discussion. Thank you, everyone, for watching us. Thank you again for your presentation. It was really great.
Bye-bye.
Bye-bye.